first speaker in this final session is Georgios Gardikis, and he's going to talk about towards software-defined QKD networks. Dr. Gardikis has 25 years of experience coordinating and contributing to research and development projects in academia and industry spanning several areas in the ICT, security, defense, and space domains. Dr. Gardikis is a project management professional, PMP certified, a senior member of the IEEE, an author or co-author of more than 80 publications in international journals and refereed conferences and workshops. Dr. Gardikis, the podium is yours.
Thank you very much. Thank you all for attending this session. I'm very glad to be here in this exciting event. So Space Hellas, the organization which I am representing, is a system integrator. So my team and myself, the R&D department, are developing solutions for integrated system monitoring, observability, security, and management. So this is the context I'm going to address in this speech, and explain what software-defined QKD networks are. So the idea of software-defined infrastructures, as you know, is around in the ICT realm for several years now. So we are talking about software-defined networks, software-defined infrastructure, software-defined radio. So the idea is to see how this term can be applied to QKD infrastructures also. So we saw today and yesterday the ability of QKD to achieve tamper-resistant key sharing. However, there are still some issues to be addressed regarding reconfigurability and flexibility. So for example, if the topology or the demand changes, we need to reconfigure everything by hand. The management platforms are proprietary and vendor specific. So if you buy a box from one vendor, then you are obliged to use the management environment of this specific vendor, and this also stands for management interfaces and data models. So with the exception of the standardization efforts which I'm going to present, the interfaces and the data models in QKD infrastructures are mostly vendor specific, and you need to search very carefully to find vendors which are interoperable with another vendor, as we saw in the demo this morning. Application onboarding. This is done manually and statically. So what do I mean by application onboarding? If we have, for example, my smartphone and I need to use a quantum key and my peer is, for example, in Athens, then I need, how is my phone how will my phone find a nearby QKD node to exchange key? How this QKD node will interact with the QKD node in my peer's location? So to date, all this is configured statically by hand. We need this to happen dynamically and on demand. QKD runs over optical infrastructure. To date, we have several management platforms for the QKD infrastructure and for the optical infrastructure. So if we really want to have QKD on demand, then this management needs to be unified. And last but not least, we have separate management from classical networks. So QKD is expected to augment a classical information network for which a management infrastructure, management environment is already in place. We would very much like to include the management of the QKD nodes in this management interface. So in a nutshell, what happens is that with the state-of-the-art, what we called FCAPS, it's a term that you probably are aware of. It's been more than 40 years in the telecom industry. It stands for Fault Configuration, Accounting, Performance, and Security. It's everything about management. So FCAPS in QKD currently is quite cumbersome. And this is where software-defined comes into play. What do we mean by software-defined QKD? So probably some of you are aware of what software-defined networking means. So the idea of software-defined networking, for example, some of you might be aware of the OpenFlow protocol. It had quite significant momentum a few years ago. Now, unfortunately, it's not adopted as it was expected, but there are other protocols and mechanisms which are in place and which are relevant. It's about decoupling what we call the control plane from the data plane. What does this mean? When we have a network of nodes and each node exchanges information with its peer nodes, then each node has the data plane, which is actually the transport of the information, and also the control plane, which is the logic. So how the information, its packet is going to be routed, how error correction will take place, how the routing tables will be maintained, and so on. So while usually in traditional networks this logic is included in each box, the idea is to centralize, to take the control plane out of the box, centralize it in a single controller, and leave the boxes only handling the data plane. This means that, for example, is what's happening in software-defined networking. For each packet arriving, then for each new flow created in the network, then each node has to interact with the controller to ask what is going to do with this flow. So the logic is centrally dictated by what we call the SDN controller. Now, you might ask, okay, how much intelligence is, at the end of the day, offloaded to this single controller? This depends on the protocols and the rationale around which software-defined networking is implemented. So this idea is being migrated to QKD networks also. So there are two standards, QKD 015 and 018. And the research teams, the standardization teams behind these two standards are coming from the telecom industry, mainly from Telefonica and other organizations, which are well aware of what software-defined is about, and are trying to apply these principles to QKD also. So QKD 15 is software-defined networking, the controller, the SDN controller for QKD. Last version was 2022, but there's an update under preparation, and this is showing that the standard is evolving. While 018 is about orchestration, we will explain later what orchestration is about. Let's start from the SDQKD concept. So in the same sense as I presented earlier, that the intelligence, the control, is outsourced to a central controller, you see here that the same principle, this figure is taken from the standard, the same principle is applied to QKD also. So the idea is to have an SDN controller which controls all these SDQKD nodes. For this to happen, it mandates that in each QKD node, you see here a node in zoom in, you need to have an agent which will interact with a controller. Okay, and this in turn will talk also with the KMS. So please don't confuse the SDN plane with the KMS plane. KMS is about key management. SDN is solely about managing the nodes and reconfiguring the nodes. Which are the main technologies behind? Those of you familiar with networks might be aware of the NetConf and YANG technologies. So YANG is a data modeling language for network configuration and monitoring data. It's nothing new. It's been around for 20 years or more. It's mainly used for managing traditional networks. And netconf is actually a communication protocol for exchanging young information. Let's have a look at these two technologies because they are really the actual enablers for making SD-QKD happen. So Young, it's a data modeling language by the ITF. It's an ITF standard, standardized, well-established, super stable. It's protocol independent in the sense that you can convey young information using different protocols, but netconf is the most prominent one, and it's extensible. Let's have a look of what young is about. Here is part of the standard. So what ETSI-QKD 015 standardizes is the interface between the SD-QKD node and the SDN controller. So what type of information can be exchanged and how this information is exchanged, how this information is modeled and how it's exchanged. Actually, QKD 015 focuses on the model, and the biggest part of the standard is this young model, and you see here how the information is structured. Okay? For example, how we represent quantities such as this is the section, for example, referring to the physical link. This is how we model the physical channel attenuation, how we model the wavelength, and the QKD role, meaning that it's either transmitter or receiver. So this information can be retrieved from the QKD node, but it can only be configured if, of course, is configurable. And this is the high-level taxonomy, which means these are the categories of information which are modeled in this standard. It's the node per se and the node capabilities. So the node needs to expose its capabilities, what it can do. The interfaces it has, the key association links, meaning the application which are using the capabilities of the node, the applications which are using the quantum keys, and any notifications which might point to an event or an error or anything like this. Here is an example how this paradigm could work. Let's consider the example we mentioned earlier, an application wanting to use the quantum keys. So you have an endpoint here, a remote endpoint somewhere else. The idea is that the two endpoints of the applications interact with the local QKD nodes, as you see here in this sequence diagram, and then it's the QKD nodes which will talk to the SDN controller. The SDN controller will match the application demands, will make sure that this is the same application, that it's authorized to use the infrastructure, to use keys, and it will create a logical path, provided, of course, that the physical path is already existent. If the physical path is not existent, then we go to orchestration. We will talk about it later. It creates a logical path between the two QKD nodes. And as this logical path is created, then the two QKD nodes know that they need to exchange keys, and they need to provide these keys. They're authorized to provide these keys to the application endpoints which are behind them. Another dimension which is very, very much facilitated by this software-defined interaction paradigm is monitoring and observability. So if you have a standardized control and monitoring interface, okay, For example, some of the devices we saw in the morning in the demo are already using SNMP. SNMP is a bit dated and it's not very convenient. It's mostly suited for management, not very convenient for configuration. So if you have a standardized control and monitor interface based, for example, on netconf and YANG, as we saw, then you can monitor and manage the entire infrastructure from a single point. In our team, we are using the Elastic Stack. I don't know if you're familiar already with this open source software stack, which is about data collection, indexing, querying, and advanced analytics. Here is a user interface of a cybersecurity platform we have built, which is built on the Elastic Stack. So the idea is to collect information in real time, collect events, collect notification, and have an integrated, what we call situational awareness of your underlying infrastructure. So if you only have 2 nodes, then it does not sound very valuable. But if we have a complex infrastructure, and if you combine this monitoring with the monitoring of the optical infrastructure, then this is becoming very, very useful, especially if you have stringent availability requirements. So why having such an enabler? The use cases are obvious: optimizing the network, forecasting, anomaly detection, which in turn facilitates cybersecurity, and predictive maintenance. You can intervene on the network before a fault actually happens. So orchestration, HC018 is a step further, is about jointly managing several SDN domains. If you have a QKD domain, a software-defined QKD domain, you can, and you have another one from another provider, and you have also a software-defined optical network, you need to jointly manage them all together to have a real on-demand service. And this is where orchestration comes into play. You see here an example, a sequence diagram, how an end-to-end QKD service can be instantiated by jointly managing the QKD infrastructure and the optical network. So you configure the QKD devices and you establish the optical path. Yes. Thank you. I'm just concluding. This is the final slide, actually. So is this actually going to, is all this actually going to happen? It sounds very nice, very appealing, but it also comes with some challenges and some considerations. The obvious challenge is security. So we asked DALI to paint a conceptual image showing the trade-off between flexibility and security, and that's what it spit out. So you have QKD, which is tamper resistant, but if you start making everything software defined, and if you start integrating it with traditional hardware and software, traditional networks and traditional software, then security holes start to pop out everywhere. Reliability and resilience is another thing. If you go to software-defined approach, then you are relying on software with whatever that means. You need to have redundant units, you need to have patches, you need to have a constant vulnerability assessment, and so on. Industry adoption is always a challenge for standards, and the standards are there, but will the vendors actually implement them? And this also has to do, this often has to do with which industries are behind the evolution of each standard, and the last question is actually about the evolution per se of the standards. So the standards are there, but will they evolve? For example, 018 is there since 2022 and there's not any update. So will it be kept live? Will it evolve? Because this is very, very crucial for the ultimate adoption of a standard. And this concludes my presentation. Thank you very much.